In this video, we're going to focus on balancing redox reactions in acidic solution. So let's start with an example. Let's say if we have the reaction between zinc and the chlorate ion, and let's say that it produces the zinc plus 2 cation and chloride. So what do you think should be the first thing that we should do in order to balance this reaction under acidic conditions? So we need to separate this reaction into half reactions. Let's write a half reaction between zinc and zinc 2 plus. Now, when balancing a half reaction, balance the atoms first, and then after that, balance the charges. So we have one zinc particle on both sides, but the charges are imbalanced. On the left side, the total charge is 0, but on the right side, the total charge is 2. So these two numbers differ by 2, so we need to add 2 electrons. Always add the electrons to the side with the higher charge. In this case, the right side. By the way, what kind of reaction do we have here? This half reaction, is it oxidation or reduction? Whenever the electrons are on the right side, it's an oxidation half reaction. Zinc is releasing or giving away electrons. Another way you can look at it is by analyzing the oxidation number. Whenever the oxidation number goes up as you travel from the left side to the right side of the reaction, it's oxidation. The zinc is being oxidized in this reaction. If the oxidation number decreased, it's reduction. Now let's move on to the next half reaction. So we have chlorate on the left side and chloride on the right side. Now before we can balance the charges, we need to balance the atoms. We have one chlorine atom on both sides, and we have 3 oxygen atoms on the left side. So we need to add 3 oxygen atoms to the right side. Under acidic conditions, you can balance such reactions by adding H plus or H2O. Since we need 3 oxygen atoms on the right side, let's add 3 water molecules, since water contains oxygen. So now the oxygen atoms are balanced. Let's move on to hydrogen. Notice that we have 6 hydrogen atoms on the right side. So we need to put a 6 on the left side. We need to add 6 H plus to that side. So now all of the atoms are balanced on both sides of the reaction. Now we can balance the charges. What is the total charge on the left side? On the left side we have 6 H plus ions, so it's 6 times 1. So we have plus 6 from those ions, and we have a negative 1 charge from the chlorate. So the total charge on the left side is positive 5. On the right side, we only have a chloride ion, so it's negative 1 on the right side. What is the difference between 5 and negative 1? 5 minus negative 1 is 6. On a number line, they're 6 units apart. So we need to add 6 electrons, but to the side with the higher charge. Since the left side has a higher charge, let's add it to the left side. Notice that for the other reaction, the electrons are on the right side. So for this one, they have to be on the left. They have to be on different sides of the reaction. They can't be on the same side, because one of the half reactions has to be oxidation and the other has to be reduction. So whenever the electrons are on the right side, it's oxidation. If they're on the left side, it's reduction. Now the next thing that we need to do is we need to make sure that both of the electrons on each reaction are equal. So we need to multiply the first half reaction by 3 so that we can get 6 electrons. So it's going to be 3 zinc atoms plus, or this is going to turn into 3 zinc plus 2 ions, and 6 electrons. Now, the other half reaction, we don't really need to change anything. But I'm going to rewrite it though. Let's get rid of that one. So in the other half reaction, we had 6 electrons, a chlorate ion, 6 H plus ions, and on the right side, it was chloride and 3 water molecules. Now that we have the same electrons, we can add the two half reactions. When you add them, the electrons will cancel since they're on opposite sides of the reaction. And then everything else, you could just bring it down. So to the left of the arrow, we have zinc, chlorate, and the H plus ions. And on the right side, we have the zinc ions, chloride, and water. So this reaction is balanced, and you can check it. We have 3 zinc atoms on both sides, 6 hydrogen atoms, 3 oxygen atoms, and 1 chlorine atom. Now the charges must balance as well. Notice that the total charge on the left side is 6 plus -1, which is 5. And here it's 3 times 2, which is 6, plus -1, and it's 5. Now let's try another example. Consider the reaction between iron metal and the permanganate ion. Go ahead and balance this reaction under acidic conditions, using what you know at this point. So just like before, let's separate it into half reactions. So let's start with iron metal. In this reaction, we have 1 Fe atom on both sides. So the number of Fe particles is the same. Now we can balance the charges. The charge on the left is 0. On the right, it's 3. These two numbers differ by 3, so we need to add 3 electrons to the side with the higher charge. So that's it for the first one. Now let's move on to the next half reaction. So we have permanganate, and it's turning into Mn plus 2. So the manganese atoms are balanced in this reaction. We need 4 oxygen atoms, so let's add 4 water molecules to the right side. Now that we have 8 hydrogen atoms, we got to add 8 H plus ions to the left side. So now that's balanced. Now we need to consider the charges. The total charge on the right side is 2. On the left, it's 8 plus -1, which is positive 7. 7 minus 2 is 5. So we need to add 5 electrons to the left side. So now the second half reaction is balanced. Now we need to make the number of electrons equal. We have 3 in the first half reaction, 5 in the second. So the least common multiple of 3 and 5 is 15. So therefore, we need to multiply the first reaction by 5 to get to 15 electrons, and the second one by 3 to get to 15. So if we multiply the first half reaction by 5, it's going to be 5 Fe and 5 Fe plus 3 and 15 electrons. Now for the second one, if we multiply everything by 3, we're going to have 15 electrons. 8 times 3 is 24, so 24 H plus ions. 3 permanganate ions, 3 of these as well, and then 4 times 3 is 12, so we need 12 H2O molecules. So now we need to add these two reactions. As we add the two reactions, the only thing that we can cancel are the 15 electrons. Now these three, we need to add them to the left side of the reaction as we add the two reactions. So it's going to be 5 Fe plus 24H plus 3 permanganate ions. And on the right side, we have these three. So it's going to be 5 Fe plus 3 on the right side, and 3 manganese ions, and 12 water molecules. So this is the balanced reaction. And to check everything, notice that we have 5 Fe atoms on both sides. We have 24 hydrogens, 12 times 2 is 24. We have 3 manganese atoms and 12 oxygen atoms on both sides. So now the last thing that we need to check is the total charge. We need to make sure it's the same on both sides. So on the left side, we have a charge of 24 and negative 3, which adds to 21. 5 times 3 is 15. 3 times 2 is 6. 15 plus 6 is 21. The total charge is 21 on both sides. So the reaction is balanced. Let's try another example. Try this one. Iodide reacts with the perbromate ion under acidic conditions to produce iodine and bromide. So let's start with the iodine ion. Now the first thing we got to do is balance the atoms. We have 2 iodine atoms on the right and 1 on the left, so let's put a 2 on the left side. Now let's balance the charges. The total charge of a pure element is 0. On the left side, it's 2 times negative 1, so we have a total charge of negative 2 on the left side. Negative 2 and 0 differs by 2, which means we need to add 2 electrons to the side with the higher charge. 0 is greater than negative 2 on the number line, so let's add it to the right side. Now the next thing we need to do is balance the other half reaction. Now we can do so by adding H plus or water. So notice that we have 1 bromine atom on both sides, but we have 4 oxygen atoms on the left. So that means we need to add 4 water molecules to the right side. So that's it for oxygen. Now let's move on to hydrogen. 4 times 2 is 8. So we need to add 8 H plus ions to the left side. Now let's check for the total charge. The total charge on the right side is -1. On the left side, it's 8 plus -1, which is +7. 7 differs from -1 by 8. 7 minus -1 is the same as 7 plus 1, which is 8. So we need to add 8 electrons to the left side. Now the next thing we need to do is make sure the electrons are equal in both half reactions. So we need to multiply the first one by 4. We don't need to change the second one, which is good. By the way, which half reaction is the oxidation half reaction and which one is the reduction half reaction? The first one is oxidation because the electrons are on the right side. The second one is reduction because the electrons are on the left side. That's how you can quickly tell which one is which. So now, let's multiply the first half reaction by 4. So we're going to have 8 iodide ions, 4 I2 molecules, and 8 electrons. So let's add these two half reactions. So as always, the electrons will cancel. So everything else, we just simply need to bring it down. So on the left side, we have these three. Now for the right side, we have everything to the right of the arrows except the 8 electrons. So we have 4 I2 molecules, a bromide ion, and 4 water molecules. So this is the balanced reaction. As you can see, we have 8 hydrogen atoms on both sides, 1 bromine atom, and 4 oxygen atoms, and 8 iodine atoms. Now let's check the total charge. The total charge on the right side is -1. On the left side, +8 and -8 cancels, so we just left with this number. So on both sides, the total charge is -1. So this reaction is balanced. So here's the last example for this video. Let's say if you have the reaction between Pb and PbO2, and under acidic conditions it turns into the Pb+2 ion. How would you balance this reaction? So let's start with the first half reaction, which is Pb turning into the Pb2+ ion. The total charge on the left side is 0, on the right side is 2, so we have to add 2 electrons to the right side, since it has a higher charge. So now let's move on to the next half reaction, PbO2. That's going to turn to Pb+2 as well. Both of these two substances, they're going to converge into the same ion. Now, before we can balance the charges, we need to balance the atoms. So we have 2 oxygen atoms on the left. That means we need to add 2 water molecules to the right side. So now that we have 4 hydrogen atoms on the right side, so let's add 4 hydrogens to the left to make it equal. Now the last thing we need to do for this half reaction is that we need to balance the charges. The total charge on the right side is +2, and on the left side it's +4. So these two numbers differ by 2, so we only need to add 2 electrons to the left side, since the left side has a higher charge. Now, because the half reactions have the same number of electrons, we don't need to modify it. So we can simply add the 2 equations. So these will cancel. On the left side, we have Pb, PbO2, and H+. So it's going to be lead metal reacting with lead dioxide plus 4H+. You can call this lead 2 oxide. I mean, not lead 2 oxide. I take that back. Lead 4 oxide. Since the charge on Pb in this particular compound is +4. Now on the right side, we have 2 Pb+2 ions. And we have 2 water molecules. So this is the final answer for this reaction. So we can see that we have 2 lead atoms on both sides of the reaction. We have 4 hydrogen atoms, 2 oxygen atoms, and that's about it. The total charge on the left side is 4, and on the right side is 4. So everything is equal for this reaction. So that's it for this video. Now you know how to balance redox reactions under acidic conditions. In this video, we're going to focus on balancing redox reactions, but within basic solutions. So what we're going to do first is we're going to balance it under acidic conditions, and then we're going to add hydroxide to both sides, and it's going to work out as if we balanced it under basic conditions. So let's begin. Let's start with this reaction. So zinc metal reacts with bromate to produce the zinc plus 2 cation and bromide. So under acidic conditions, what's the first thing we should do to balance this reaction? So the first thing we need to do, we need to separate this reaction into two half reactions. So let's start with zinc. Zinc is going to convert into the zinc plus 2 cation. Now the number of particles, or zinc particles, they're already balanced. We have one zinc particle on each side. So we need to balance the charge. The charge on the right side is 0, but the charge on the left side is plus 2. So the difference between these two numbers is 2. So we need to add 2 electrons, but we're going to add it to the side with the higher charge. So we're going to add it to the right. If we do that, the net charge on the left side and on the right side will be the same. It's going to equal a charge of 0. So now, let's balance the second half reaction. So bromate converting into bromide. Now to balance this half reaction under acidic conditions, we are allowed to add H plus and H2O to balance the atoms first. So we have 3 oxygen atoms on the left. Therefore, we're going to add 3 water molecules to the right side so that the number of oxygen atoms are the same. So we have 3 oxygen atoms on both sides right now. But by adding 3 water molecules, we've added 6 hydrogen atoms to the right side. So we need to add 6 H plus ions to the left side. Now once the number of particles or atoms are balanced on both sides, we can now balance the charges by adding electrons. The total charge on the right side is -1. The total charge on the left side, so we have 6 hydrogens each with a +1 charge. So 6 times 1 is +6, plus the negative charge from the bromate ion. So 6 and -1, the net charge on the left side is +5. So the difference between 5 and -1, if we subtract those two numbers, 5 minus -1, the difference is +6. So we need to add 6 electrons to the side with the higher oxidation state, or the higher charge. In this case, the left side. So now we've balanced the second half reaction. So now what do we need to do at this point? At this point, we need to balance the number of electrons. So notice that we have 6 electrons on the left and 2 electrons on the right. So let's multiply this equation by 3. So it's going to be, we're going to have 3 zinc atoms, 3 zinc cations, and now we're going to have 6 electrons. So if we add these two equations, the number of electrons will cancel. And so it's going to be 3Zn plus 6H plus Br, this is a 3, BrO3 minus, and that's going to turn into 3Zn plus 2 plus Br minus plus 3 water molecules. So this is the balanced reaction under acidic conditions. Now to get the answer under basic conditions, what we're going to do is we're going to add 6 hydroxide ions to both sides. The reason why we're going to add 6 is because we have 6 H plus ions. H plus OH minus will give you H2O. So let's add 6 hydroxides to the left side, and let's add 6 hydroxides to the right side. So on the left, we're going to have 3 zinc atoms. Now 6H plus 6 hydroxide ions is equal to 6 water molecules. And then we're going to have 1 bromate ion. and on the right it's still going to be 3Zn2 plus Br minus, but we're also going to have 6 hydroxide ions and 3 H2O molecules. So now what we're going to do is we need to subtract both sides by 3 water molecules. Notice that we have H2O on both sides. So on the left side we're going to take away 3 water molecules, and on the right side we're going to take away 3. If you want to know why it's 3, you look at the number of water molecules on both sides. We have 6 on the left, 3 on the right, and then you want to subtract it by the smaller of these two values. So now we have our final answer, which is 3Zn plus 3H2O plus BrO3 minus bromate and 3 zinc 2 plus cations plus 6 hydroxide ions plus Br minus. So that's how you can balance a reaction under basic conditions. So if you notice, we have 3 zinc atoms on both sides. We have 6 hydrogen atoms, 1 bromine atom, and notice that we have a total of 6 oxygen atoms. 6 here, 3 in bromate, and 3 in water. So all of the atoms are balanced, and if you look at the net charge, notice that the net charge on both sides is the same. On the left side, the net charge is -1. On the right side, we have 3 times plus 2, which is plus 6, 6 times -1, which is -6, plus 6 and -6 is 0, and then we have a -1 charge from the bromide ion. So on both sides, the net charge is -1. So we know this reaction is balanced. The number of atoms are the same on both sides, and the total charge is the same on the left side and on the right side. So now let's try another example. So iron metal reacts with the perchlorate ion to produce Fe plus 3, or 3 plus the chloride ion. So go ahead and balance this reaction under basic conditions. Feel free to pause the video, try this example yourself, and then unpause it when you're ready. See if you get the right answer. So what we're going to do first is we're going to balance it under acidic conditions. So let's start with Fe. Fe turns into Fe plus 3. And we need to add 3 electrons to the right side to balance the charge. So we're done with that half reaction. Now let's start with the next half reaction. So perchlorate is going to turn into chloride. Now we're going to balance this under acidic conditions first. So we're going to start by adding water molecules. How many water molecules do we need to add to this reaction, and to which side should we add it to? Notice that we have more oxygen atoms on the left side. So we're going to add 4 water molecules on the right side so that the number of oxygens are balanced. But now notice that we have 8 hydrogen atoms on the right side. So we need to add 8 hydrogen atoms to the left side. So we're going to add it in the form of 8 H plus ions. Now the last thing we need to do for this half reaction is that we need to balance the number of electrons. So let's find the total charge on each side. On the right side, the total charge is -1. On the left side, we have 8 times 1, which is plus 8, plus the -1 charge from the perchlorate ion. So we have a net charge of +7 on the left side and -1 on the right side. So if we subtract these two numbers, 7 minus -1, that's the same as 7 plus 1. So the difference between these two numbers is 8, which means that we need to add 8 electrons to the second half reaction. So to which side should we add those 8 electrons? To the left side or to the right side? So keep in mind, always add the electrons to the side with the higher charge. So we're going to add it to the left side. And in the other half reaction, notice that the electrons are on the right side. So therefore, in the second half reaction, it has to be on the left side. They cannot both be on the same sides. Whenever the electrons are on the right side, the reaction is oxidation. You have an increase in oxidation state from 0 to +3, and you can see that iron is losing 3 electrons because it's on the right side. Whenever the electrons are on the left side, you have a reduction half reaction because it involves a gain of electrons. And notice that the oxidation state of chlorine decreases from 7 to -1, so it's a reductive process. Now that we have each half reaction balanced, Now what we need to do next is we need to balance the number of electrons because they're unequal for this reaction. So how can we do that? So we have 3 electrons in the first half reaction and 8 in the second. The least common multiple between 3 and 8 is 24. So we're going to multiply the first one by 8 and the second one, or the second half reaction, by 3. So then what we're going to have now is going to be 8 Fe and 8 Fe3 plus 24 electrons. And here we're going to have 24 H plus 3 perchlorate ions plus 24 electrons, which is going to give us 3 chloride ions and 12 water molecules. So now what we're going to do is we're going to add the 2 half reactions together. But let's make some space first. The number of electrons is going to cancel. And so on the left, we're going to have 8 iron atoms plus 24 H plus ions and 3 perchlorate ions and 8 Fe3 plus cations and 3 chloride ions, and finally 12 H2O molecules. So notice that this reaction is balanced. We have 24 hydrogen atoms on both sides, 3 chlorine atoms, 12 oxygen atoms, and 8 iron atoms. And if we check the total charge, let's make sure it's the same on both sides. Here, this is plus 24, negative 3, and let's see, 8 times 3 is also 24, and we have a minus 3 from the 3 chloride ions. So as we can see, the total charge is the same on both sides. So we have the balanced reaction under acidic conditions. So now we wish to balance it under basic conditions. So what can help us to do that? What do we need to do at this point? At this point, we need to add hydroxide ions to the solution. So the number of hydroxide ions that you need to add is based on the number of H plus ions that you see in a balanced reaction. So we're going to add 24 hydroxide ions to both sides of this equation. So on the left side, 24 H plus 24 hydroxides is going to give us 24 water molecules. So we're going to have 8 Fe plus 24 H2O molecules, and then everything else is going to be the same. But on the right side, we're going to have an extra 24 hydroxide ions. Okay, so now, what is the next thing that we need to do? What's our next step? Notice that we have water on both sides, so we're going to subtract both sides by the smaller of these two values. So 12 is smaller than 24. So we're going to subtract both sides by 12 H2O molecules. So on the right side, H2O is going to disappear completely. So now we can write our final answer. So it's going to be 8 Fe plus 12 H2O plus 3 perchlorate ions, which yields 8 Fe3 plus cations plus 3 chloride ions, and then plus 24 hydroxide ions. So now it's balanced. This is our final balanced reaction under basic conditions. So we can see that we have 8 iron atoms on both sides. Here we have 3 times 4, 12 oxygen atoms, plus 12 here, and we have 24 oxygen atoms in the 24 hydroxide ions. And we have 3 chlorine atoms on both sides, and 12 times 2 is 24 hydrogen atoms. So the number of atoms are the same. Now let's check the net charge. The net charge on the left side is 3 times -1, so it's -3. On the right side, we have 8 times 3, which is plus 24, which cancels with the -24 from the 24 hydroxide ions. And we have a -3 charge from the 3 chloride ions. So the number of atoms and the charges are the same. So this is it. This is the final answer.
The Earth's atmosphere is the layers of the gases which protects the Earth from the radiations and cosmic rays coming from the outer space. This atmosphere acts as a blanket because it keeps the average temperature of the Earth nearly constant. Earth's atmosphere can be divided into 5 main layers. These layers are the troposphere, the stratosphere, the mesosphere, the thermosphere, and the exosphere. The troposphere. Tropos means change. This layer gets its name from the weather that is constantly changing and mixing up the gases in this part of our atmosphere. This layer is the closest to Earth's surface. On average, the troposphere extends from the ground to about 12 kilometers or 7.5 miles high. The troposphere contains about 75% of all of the air in the atmosphere and almost all of the water vapor, which forms clouds and rain. In this layer, air is made up of approximately 78% nitrogen, 21% oxygen, and 1% argon, with small amounts of additional gases, including water vapor and carbon dioxide. Hot air balloons fly within the troposphere. The stratosphere. Strat means layer. This layer of our atmosphere has its own set of layers. The boundary between the stratosphere and the troposphere is called the tropopause. It is the region where airplanes fly. The stratosphere layer extends from the tropopause to about 50 kilometers or 32 miles above the Earth's surface. This layer contains a thin layer of ozone molecules, which forms a protective layer and absorbs harmful ultraviolet radiation from the sun. The high-altitude weather balloons flying into the stratosphere for monitoring atmospheric conditions and climate research. The mesosphere. Meso means middle. This layer is located above the stratosphere and below the thermosphere. It is the third layer in our atmosphere, which is 35 kilometers or 22 miles thick. The transition boundary, which separates the mesosphere from the stratosphere, is called the stratopause. In the mesosphere, fewer air molecules to absorb incoming electromagnetic radiation from the sun. Most meteors burn up in this atmospheric layer. A meteor is a piece of rock or matter that has been broken off in space and travels through the atmosphere. When they cross the mesosphere, friction and momentum cause the meteor to burn up and appear as a light crossing the sky. The thermosphere. Thermo means heat. This layer has extremely high temperatures and located above the mesosphere and below the exosphere. The boundary between the mesosphere and the thermosphere atmospheric regions is called mesopause. It is the coldest part of Earth's atmosphere. The thermosphere extends from the mesopause to 700 kilometers of 435 miles above the surface of the Earth. The thermosphere is the thickest layer in the atmosphere. Only the lightest gases, mostly oxygen, helium, and hydrogen, are found here. The aurora and satellites mostly occur in this layer. An aurora is a natural light display in the sky, particularly in the high-latitude regions, that is caused by the collision of energetic charged particles with atoms in the high-altitude atmosphere. The exosphere. Exo means outside. The exosphere represents the outermost layer of Earth's atmosphere. It extends from the top of the thermosphere to 10,000 kilometers or 6,214 miles above Earth's surface. In this layer, atoms and molecules escape into space, and higher altitude satellites orbit our planet. Temperature versus height. Near the surface of the Earth, the average temperature is 15 degrees Celsius, and the temperature gradually decreases to -56 degrees Celsius as altitude increases. Then the temperature remains constant below ozone layer. in the stratosphere region, from the ozone layer the temperature progressively increases to -2 degrees Celsius. Then, the temperature ranges from -2 degrees Celsius to -92 degrees Celsius, at the upper boundary of mesosphere. After then, the temperature rises from -92 degrees Celsius to 1200 degrees Celsius, near the upper boundary of thermosphere. Why it happens? During the day, a portion of the incoming of the radiant energy from the sun passes through the atmosphere, is absorbed and warms the Earth's surface. Then, the heat's reflected back from the ground to the tropospheric air by conduction and convection process. The temperature in the troposphere gradually decreases with increasing altitude until the tropopause is reached. The stratosphere is very dry, and clouds are rare. As we know, ozone is concentrated in this part of the atmosphere. This ozone absorbs short-wave ultraviolet radiation from the sun and converts them into heat. More radiation is absorbed at higher altitudes compared to the lower stratosphere, so the temperature increases with height. The mesosphere has the coldest temperatures in the atmosphere. It becomes cold enough to freeze water vapor in its atmosphere into ice clouds. The air density in the mesosphere is low than in the stratosphere below. Due to less air particles, not enough heat is absorbed, which eventually leads to a colder temperature. Apart from that, carbon dioxide in the mesosphere also helps in making this layer cold due to its cooling effect. Carbon dioxide molecules absorb heat energy when they bounce off other molecules. The carbon dioxide releases some of that energy as photons in a process called radiative emission. Some of those photons travel upwards, carrying heat away from the mesosphere. Thus, temperature in the mesosphere keeps dropping with increase in altitude until it reaches about -100 degrees Celsius. The thermosphere has extremely high temperatures. Within the thermosphere, temperatures rise continually to well beyond 1000 degrees Celsius. The source of the thermosphere's heat is radiation emitted by the sun. The thermosphere absorbs much of the radiation that Earth receives from the sun, leaving only a fraction to actually reach the surface. Ultraviolet radiation, visible light, and high-energy gamma radiation are all absorbed by the thermosphere. Since there is little to no atmospheric gases above the thermosphere, there is no absorption of the heat from solar radiation, and so temperatures soar. The exosphere is almost a vacuum. The air is very, very thin air. When air is thin, it doesn't transfer much heat to objects in the air, even if the air is very, very hot. The temperature in the exosphere varies greatly and can range from 0 to over 1,700 degrees Celsius. It is colder at night and much hotter during the day.
In order for plants to grow, they need inputs of carbon dioxide, water, and energy. The chemical process by which plants use these resources to manufacture glucose, the building blocks of plants, is called photosynthesis. In the process, oxygen gas is produced as a byproduct. The energy for photosynthesis originates in the sun and arrives at the earth as sunlight. This light has both a wave and a particle nature. The particles, or photons, are the smallest units of light. Photons oscillate along a path, which is measured as wavelengths. The light emitted from the sun contains photons in a wide spectrum of wavelengths, called the electromagnetic spectrum. Photosynthetic organisms use only a small portion of the electromagnetic spectrum, called visible light. Photosynthetic organisms contain pigments that facilitate the capture of wavelengths of light in the visible light range. The color of the pigment comes from the wavelengths of light reflected. Plants appear green because they reflect yellow and green wavelengths of light. Red and blue wavelengths of light are absorbed by these pigments and provide the energy that is used for photosynthesis. Within eukaryotic photosynthetic organisms, also known as photoautotrophs, the chemical reactions of photosynthesis occur within plant cells in specialized structures known as chloroplasts. Photosynthesis consists of two sets of reactions: the light-dependent reactions and the Calvin cycle. Within the chloroplast are small disc-like structures called thylakoids, which are surrounded by a fluid-filled space called the stroma. The reactions that synthesize glucose, the Calvin cycle, occur in the stroma. The light-dependent reactions occur in the thylakoid. It is here that conversion of light energy to chemical energy is initiated. In most photosynthetic organisms, thylakoids contain pairs of photosystems, called photosystem 1 and photosystem 2, that work in tandem to produce the energy that will later be used in the stroma to manufacture sugars. The photosystems of the thylakoid consist of a network of accessory pigment molecules and chlorophyll, the molecules that absorb the photons of light. Within the pigment molecules, the absorbed light energy excites electrons to a higher state. Photosystems will channel the excitation energy gathered by the pigment molecules to a reaction center chlorophyll molecule, which will then pass the electrons to a series of proteins located on the thylakoid membrane. Photons of light strike photosystems 1 and 2 simultaneously. We will examine what happens with the photons striking photosystem 2 first. The energized electrons are passed from the reaction center of photosystem 2 to an electron transport chain. The electrons lost by photosystem 2 are replaced by a process called photolysis, which involves the oxidation of a water molecule producing free electrons and oxygen gas. While this oxygen gas is a byproduct of photosynthesis, it is an important input to the cellular respiration pathways. As electrons pass through the electron transport chain, the energy from the electron is used to pump hydrogen ions from the stroma to the thylakoid, creating a concentration gradient. This gradient powers a protein called ATP synthase, which phosphorylates ADP to form ATP. The low-energy electrons leaving photosystem 2 are shuttled to photosystem 1. Within photosystem 1, low-energy electrons are re-energized and are passed through an electron transport chain where they are used to reduce the electron carrier NADP+ to NADPH. When the chloroplast is receiving a steady supply of photons, NADPH and ATP molecules are rapidly being provided to the metabolic pathways in the stroma. Therefore, the ATP and NADPH formed during the light-dependent reactions are used in the stroma to fuel the Calvin cycle reactions. The Calvin cycle consists of a series of reactions that reduce carbon dioxide to produce the carbohydrate glyceraldehyde 3-phosphate. The cycle consists of 3 steps, the first of which is carbon fixation. In this step, carbon dioxide is attached to ribulose 1,5-bisphosphate, resulting in a 6-carbon molecule that splits into 2 3-carbon molecules. The second step is a sequence of reactions using electrons from NADPH and some of the ATP to reduce carbon dioxide. In the final step, ribulose 1,5-bisphosphate is regenerated. For every 3 turns of the cycle, 5 molecules of glyceraldehyde 3-phosphate are used to reform 3 molecules of ribulose 1,5-bisphosphate. The remaining glyceraldehyde 3-phosphate is then used to make glucose, fatty acids, or glycerol. It takes 2 molecules of glyceraldehyde 3-phosphate to make 1 molecule of glucose phosphate. Thus, the Calvin cycle has to run 6 times to produce 1 molecule of glucose. These molecules can remove their phosphate and add fructose to form sucrose, the molecule plants use to transport carbohydrates throughout their system. Glucose phosphate is also the starting molecule for the synthesis of starch and cellulose. Plants produce sugars to use as storage molecules and structural components for their own benefit. By utilizing the energy of the sun, along with inputs of water and carbon dioxide, plants act as glucose factories. Photosynthetic organisms are the primary producers of glucose on the planet. They also produce oxygen gas as a byproduct, and thus serve as the foundation of life, providing food and oxygen for the complex food webs on both land and in the oceans.
Every time you smoke a cigarette, toxic gases pass into your lungs, then into your bloodstream, where they spread to every organ in your body. A cigarette is made using the tobacco leaf, which contains nicotine and a variety of other compounds. As the tobacco and compounds burn, they release thousands of dangerous chemicals, including over 40 known to cause cancer. Cigarette smoke contains the poisonous gases carbon monoxide and nitrogen oxide, as well as trace amounts of cancer-causing radioactive particles. All forms of tobacco are dangerous, including cigars, pipes, and smokeless tobacco such as chewing tobacco and snuff. Nicotine is an addictive chemical in tobacco. After you inhale tobacco smoke, nicotine flows through the bloodstream to your brain, where it induces a pleasurable feeling. When you repeatedly expose your brain to nicotine, it becomes desensitized, making you crave more and more nicotine just to feel normal. Smoking causes death. People who smoke typically die at an earlier age than non-smokers. In fact, 1 of every 5 deaths in the United States is linked to cigarette smoking. If you smoke, your risk of major health problems increases dramatically, including heart disease, heart attack, stroke, lung cancer, and death from chronic obstructive pulmonary disease. Smoking causes cardiovascular disease. When nicotine flows through your adrenal glands, it stimulates the release of epinephrine, a hormone that raises your blood pressure. In addition, nicotine and carbon monoxide can damage the lining of the inner walls in your arteries. Fatty deposits, called plaque, can build up at these injury sites and become large enough to narrow the arteries and severely reduce blood flow, resulting in a condition called atherosclerosis. In coronary artery disease, atherosclerosis narrows the arteries that supply the heart, which reduces the supply of oxygen to your heart muscle, increasing your risk for a heart attack. Smoking also raises your risk for blood clots because it causes platelets in your blood to clump together. Smoking increases your risk for peripheral vascular disease, in which atherosclerotic plaques block the large arteries in your arms and legs. Smoking can also cause an abdominal aortic aneurysm, which is a swelling or weakening of your aorta where it runs through your abdomen. Smoking damages two main parts of your lungs: your airways, also called bronchial tubes, and small air sacs called alveoli. With each breath, air travels down your windpipe, called the trachea, and enters your lungs through your bronchial tubes. Air then moves into thousands of tiny alveoli, where oxygen from the air moves into your bloodstream, and the waste product carbon dioxide moves out of your bloodstream. Tiny hair-like projections, called cilia, line your bronchial tubes and sweep harmful substances out of your lungs. Cigarette smoke irritates the lining of your bronchial tubes, causing them to swell and make mucus. Cigarette smoke also slows the movement of your cilia, causing some of the smoke and mucus to stay in your lungs. While you are sleeping, some of the cilia recover and start pushing more pollutants and mucus out of your lungs. When you wake up, your body attempts to expel this material by coughing repeatedly, a condition known as smoker's cough. Over time, chronic bronchitis develops as your cilia stop working, your airways become clogged with scars and mucus, and breathing becomes difficult. Your lungs are now more vulnerable to further disease. Cigarette smoke also damages your alveoli, making it harder for oxygen and carbon dioxide to exchange with your blood. Over time, so little oxygen can reach your blood that you may develop emphysema, a condition in which you must gasp for every breath and wear an oxygen tube under your nose in order to breathe. Chronic bronchitis and emphysema are collectively called chronic obstructive pulmonary disease, or COPD. COPD is a gradual loss of the ability to breathe, for which there is no cure. Cigarette smoke contains at least 40 cancer-causing substances called carcinogens, including cyanide, formaldehyde, benzene, and ammonia. In your body, healthy cells grow, make new cells, then die. Genetic material inside each cell, called DNA, directs this process. If you smoke, toxic chemicals can damage the DNA in your healthy cells. As a result, your damaged cells create new unhealthy cells, which grow out of control and may spread to other parts of your body. The most common cancer in the world is lung cancer, with over 1 million new cases diagnosed every year. Harmful chemicals in cigarettes can cause cancer in other parts of your body, such as in the blood and bone marrow, mouth, larynx, throat, esophagus, stomach.
Acid rain sounds like something straight out of a sci-fi film, like strange raindrops that fall on a city and corrode everything. The truth is not far off, but the good news is that we know a lot about what causes acid rain and how to address its impact on the environment, our bodies, and the built world. Interestingly, normal rain is actually slightly acidic as well. If you think back to the pH scale, you'll remember that it goes from 0 to 14, acidic to basic, and that 7, right in the middle, is neutral. Normal rain is around 5 or 5.5, so it's slightly acidic. But acid rain is even more acidic and typically around a pH of 4. Now, this might not sound like a big difference, but remember that this is a logarithmic scale. So each increment, like from 4 to 5, is actually a tenfold difference. So if we're comparing normal rain at about 5.5 and acid rain at 4, that's a pretty big deal. So now the questions are, how does acid rain form? Why does it matter? And what effects can acid rain have on our communities? So the short answer to how it forms is pollution. So let me try to bring that to life for you with my imaginary hand-drawn city. Now remember that most of the fuels we burn to make energy are from fossil fuels, so that animal and plant matter that has been in the ground for millions of years. And when we burn these fuels, they tend to have remaining traces of sulfur in them, especially coal. And both coal and oil burn at such high temperatures that they can cause nitrogen and oxygen in the air to form different compounds. So imagine we have here an oil refinery and a coal burning plant and a lot of cars. A common byproduct of coal burning plants or smelters and other industrial facilities is sulfur dioxide, SO2. At the same time, high temperatures from combustion engines and oil refineries provide enough energy to break apart nitrogen and oxygen molecules in the air. These molecules can then recombine to form different nitrogen oxides, like nitric oxide, NO, and nitrogen dioxide, NO2. Together, these are referred to as nitrogen oxides, which you can abbreviate by NOx. So the same can be said about sulfur dioxide. That falls into the category of sulfur oxide, SOx or SOx. So a fun way to remember the precursors to acid rain are SOx and NOx. Now, these precursors belonging to the SOx and NOx family are hanging out up in the air. When they interact with UV radiation from the sun and water molecules that are also in the air, they form different vapors. These acid vapors, sulfuric acid vapor, H2SO4, and nitric acid vapor, HNO3. And these acids are no joke. Sulfuric acid is highly corrosive. It can burn your skin, the vapors can irritate your respiratory tract, and nitric acid is known to be used in explosives and rocket launches. And these are the acids that make up the phenomenon of acid rain. Over time, these smokestacks have actually gotten taller. One example in the early 1970s, when the EPA wanted to reduce emissions from these coal-burning facilities and oil refineries, to control the air quality around those communities, what these facilities did was build larger smokestacks or taller smokestacks so that those pollutants would disperse and spread out over a larger area and not fall over the local community as much or as fast. Instead, what ended up happening is that these pollutants were carried by the wind to communities and natural environments downwind of where they were being created, up to 1,000 kilometers or over 600 miles. And when these acid vapors cause acid rain, it's not always rain like we think of with water falling from the sky. Acid rain is just a general term, and it really includes all forms of precipitation, like snow, fog, cloud vapor, and dry deposition like dust particles. And also, it can have different combinations of these forms. And now the other big question is, why does it matter, right? How are we affected? And also, Does that acid burn your skin? A very logical thing to want to know. So for cities, first of all, acid rain is bad news because it can damage buildings and statues, particularly those that are made of limestone, marble, and some metals. Here in this photo is a gargoyle from the Munich town hall, which is almost unrecognizable because of all of the damage it sustained from acid rain. There's also been a lot of studies over the years looking at the US Capitol and a lot of the surfaces there that are made of marble and how they can strengthen them to protect them from acid rain before it's too late. Now, if we go a little deeper, acid rain can leach or pull out heavy metals like aluminum from the soil or rocks, which can then be washed out to lakes and, as you can imagine, can lead to a lot of bad things like contaminating drinking water and harming aquatic ecosystems. Many fish can't survive at a lower pH. Acid rain also has impacts on other natural environments, especially because of how far its reaches. Acid rain can damage and weaken forests and trees by stripping nutrients from the soil and even damaging the waxy outer coat, leaving them much more vulnerable to losing more nutrients. Now, when it comes to humans, these acid vapors and the different precipitation that they create are very harmful to our respiratory system, and especially those that have asthma. And of course, I have to answer the question, does acid rain burn your skin? The answer is no, it's just not acidic enough. Remember, acid rain is around a pH of 4, and for something to burn your skin, it has to be much more acidic, usually around a pH of 1. There is some good news when it comes to acid rain. In 1990, the EPA created the Acid Rain Program to help power plants reduce emissions. In 2019, when they looked at the levels compared to 1990, they saw pretty great reductions. A 94% reduction in sulfur dioxide and an 86% reduction in nitric oxides. Now, this is in the United States, but around the world, acid rain is still a problem, particularly
reaction is in chemical equilibrium because the speed of forward reaction is equal to the speed of backward reaction. Here, let me ask you an important question which I often ask. What is meant by disturbing chemical equilibrium? Well, when we say disturbing chemical equilibrium, it means that we are disturbing or changing the speed of either forward reaction or backward reaction. So remember that whenever I say disturbing the chemical equilibrium, it means that I am disturbing the speed of either side. Now the second question is, how can we disturb the chemical equilibrium? Basically, there are 3 methods through which we can disturb any chemical equilibrium. Firstly, change the concentration of reactants and products. Secondly, changing the temperature of a system. And thirdly, changing the pressure of a system. Thus remember that we can disturb the chemical equilibrium by 3 different ways. Now what is Le Chatelier's principle in simple words? Well, consider the previous example. Let this reaction is in chemical equilibrium. Now I am interested to disturb the chemical equilibrium. Let's consider that I add one another atom of X and one another atom of Y. So I have changed the concentration of reactants. Now this system will respond to this change of concentration of reactants. Let me repeat it. This system will respond to this change of concentration of reactants. Here, the change is simple. I mean, the concentration of reactants is large and the concentration of product is small. So what will be the response of this system? It is very simple. The rate of forward reaction will become high to make more products. Now the rate of forward reaction is higher than the rate of backward reaction, or we say that equilibrium is shifted in forward direction. Lastly, when 2 molecules are completely formed, the system will restore its chemical equilibrium. I mean, the rate of forward reaction becomes equal to the rate of backward reaction because 4 atoms react together to form 2 molecules and 2 molecules back down to form 4 atoms. Now listen carefully. Overall, We learned that if we disturb the chemical equilibrium of a reversible reaction, it will respond to the change and will restore its chemical equilibrium. Let me repeat it. If we disturb the chemical equilibrium of a reversible reaction, it will respond to the change and will restore its chemical equilibrium. This is what the Le Chatelier's principle state. So note it down, this super easy definition of Le Chatelier's principle, which is often made very difficult. Now let me teach you my personal trick of Le Chatelier's principle. For example, consider these reversible reactions. Now what will happen if we increase the concentration of hydrogen gas in this case and decrease the concentration of nitrogen gas in this case? Well, I use my personal trick. Let X atom and Y atom react together to form XY molecule, and XY molecule breaks down to form XY atoms. Now listen carefully. When we increase the concentration of hydrogen gas, it means that we are adding more hydrogen gas. Here, if I ask you what is changed, your answer is simple. There are more reactants and less product. Secondly, if I ask you what is the response of this system, your answer is again simple. The equilibrium will proceed in forward direction to form more products and neutralize the effect of concentration. Let me repeat it. The equilibrium will proceed in forward direction to form more products and neutralize the effect of concentration. Therefore, remember that if we increase the concentration of the hydrogen gas, equilibrium will shift in forward direction to neutralize the effect and restore chemical equilibrium. Secondly, I again write X and Y atoms. They react together to form XY molecule. Now listen carefully. When we decrease the concentration of nitrogen gas, it means that we are reducing or removing nitrogen gas. Here, if I ask you what is changing and what is the response of the system, your answer is simple. There are more products and less reactants. Secondly, the equilibrium will proceed in backward direction in order to form more reactants and neutralize the effect. Therefore, if we decrease the concentration of nitrogen gas, equilibrium will shift in backward direction to neutralize the effect and restore chemical equilibrium. Thus, using this trick, we can easily calculate the equilibrium shift if concentration is changed. Now let me teach you the effect of changing pressure on chemical equilibrium. Here, remember that changing pressure only affects reversible reactions if reactants and products are in gaseous state. Now consider these reactions. What will happen if we increase the pressure in this case and decrease the pressure in this case? Well, on the left side, there is 1 mole of PCl5, while on the right side, there is 1 mole of PCl3 and 1 mole of chlorine gas. So I write 1 mole of reactants and 2 moles of products. Now here, the trick is that we only consider larger number. We can see that the larger number is 2 mole. Now listen carefully. When we increase the pressure, it means that we are increasing the number of 2 moles further and putting more pressure. Let me repeat it. When we increase the pressure, it means that we are increasing the number of 2 moles further and putting more pressure. So here, the change is more pressure on products and less pressure on reactants. Can you guess the response of this system? Well, it is simple. The equilibrium will proceed in backward direction to counter the effect of pressure and restore chemical equilibrium. Secondly, in this case, we already know that there is 1 mole of reactants and there are 2 moles of products. We know that we only consider the larger number. Here, the larger number is 2. Now when we decrease the pressure, it means that we are decreasing the number of 2 moles further and putting less pressure on reactants. Let me repeat it. When we decrease the pressure, it means that we are decreasing the number of 2 moles further and putting less pressure on reactants. So here the change is less pressure on products and more pressure on reactants. Thus the response will be the equilibrium will proceed in forward direction to counter the effect of pressure. Therefore, remember that decreasing pressure means that equilibrium will shift in forward direction. So using this simple trick, we can easily calculate the effect of change of pressure on chemical equilibrium. Here, let me teach you one bonus question. Consider this reversible reaction. What will be the effect of increasing or decreasing pressure? Well, the answer is simple. Increasing or decreasing pressure has no effect on this chemical reaction because the number of moles of reactants is 2 and the number of moles of products is also 2. So note it down that if the number of moles of reactants is equal to the number of moles of products, changing pressure doesn't affect the chemical equilibrium. Finally, let me teach you the effect of changing temperature on chemical equilibrium. Remember that if heat of enthalpy del H is negative, it is an exothermic reaction in which heat is given off to the surrounding. While if heat of enthalpy del H is positive, it is an endothermic reaction in which heat is absorbed from the surrounding. Now consider these reversible reactions. What will happen if we decrease temperature in this case and increase temperature in this case? Well, we know that this is endothermic reaction. In case of endothermic reaction, I always write here cold and I write here hot. Here, the trick is we only consider the hot side and we do not look at the cold side. Now listen carefully. If we decrease the temperature, it means that we are cooling the hot side or removing heat from the hot side. Let me repeat it. If we decrease the temperature, it means that we are cooling the hot side or removing heat from the hot side. So the change is product becomes cold and reactants become hot. Now the response is equilibrium will proceed in forward direction in order to produce more reactants to counter the effect of temperature. Secondly, in this case, we know that the enthalpy of heat is negative, so it is an exothermic reaction. In case of exothermic reaction, I always write here hot and I write here cold. Now listen carefully. If we increase the temperature, it means that we are adding more heat to the hot side. Let me repeat it. If we increase the temperature, it means that we are adding more heat to the hot side. So the change is reactant becomes hot and products become cold. Thus the response of the system will be equilibrium will shift in forward direction in order to produce more products to counter the effect of temperature. Therefore, if we increase the pressure, the equilibrium will shift in forward direction. Thus note down these examples. Lastly, let me teach you one bonus question. Why adding catalyst cannot affect the position of equilibrium? Well, it is because the catalyst speeds up the forward and the backward reaction to the same extent. So adding catalyst only speeds up the forward and backward reaction. It doesn't change the position of equilibrium. I hope that you have learned all about Le Chatelier's principle.
pH and pOH, ionic product of water. Why ionic product of water is equal to 10 to the power negative 14, and proof that pH plus pOH is equal to 14. Firstly, let me teach you that what is ionic product of water. Well, consider water in this object at 25 degrees centigrade. Let there are 10 millions of water molecules present in it. Now listen carefully. It is experimentally proved that out of 10 millions molecules of water at 25 degrees centigrade, only one molecule ionizes into hydrogen ion and hydroxide ion. If you think that why the rest of molecules do not ionize, then the answer is simple. It is because water is a stable compound. So only one molecule ionizes into hydrogen ion and hydroxide ion. This ionization of water molecule is called self-ionization or auto-ionization of water. Now in this object, there are two things. I mean 10 million molecules of water and ion of hydrogen and ion of hydroxide. So we say that water is present in larger quantity. It is a solvent. Both ions, hydrogen and hydroxide, are present in smaller quantity, so they are solute. Now let me ask you, do you know the formula of concentration? Well, concentration is the ratio of amount of solute to the amount of solvent. Now let me find the concentration of hydrogen ion in the water. I write hydrogen ion in the square bracket. Remember that square bracket means concentration. We know that only one hydrogen ion is present in 10 million molecules of water. Our hydrogen ion concentration is equal to 1 upon 10 to the power 7. Here, I will shift 10 to the power 7 from the denominator to numerator. So the power becomes negative 7. I get hydrogen ion concentration is equal to 1 into 10 to the power negative 7. Secondly, let me find the hydroxide concentration in the water. We write hydroxide ion concentration is equal to, there is only one hydroxide ion present in 10 million molecules of water. Our hydroxide ion is equal to 1 upon 10 to the power 7. Now I shift 10 to the power 7 from the denominator to numerator. The sign of 7 becomes negative. I get concentration of hydroxide ion is equal to 1 into 10 to the power negative 7. So the concentration of hydrogen ion and the concentration of hydroxide ion is the same. We know that pure water is neutral. It means that water is neither acidic nor basic, because the concentration of hydrogen ion and hydroxide ion is the same. Now let me derive the value of Kw, or ionic product of water. We have already learned about the self-ionization of water. Let me write Kc, or equilibrium constant value for this reaction. As we know that Kc is equal to product of concentration of products to the product of concentration of reactants. Here, H2O is reactant, hydrogen ion and hydroxide ion are products. So I write Kc is equal to concentration of hydrogen ion and to concentration of hydroxide ion upon concentration of water. Now I will shift the concentration of water from the right hand side to the left hand side, and I get this equation. The concentration or amount of water is constant. I mean, there are fixed 10 million molecules of water. So instead of Kc into concentration of water, I write Kw, which is called ionic product of water, and it is equal to concentration of hydrogen ion and to concentration of hydroxide ion. We know that the concentration of hydrogen ion in 10 million molecules of water is 1 into 10 to the power negative 7. And that of hydroxide ion is also 1 into 10 to the power negative 7. So I write Kw is equal to 1 into 10 to the power negative 7 into 1 into 10 to the power negative 7. I get Kw is equal to 1 into 10 to the power negative 14, or I can also write Kw is equal to 10 to the power negative 14. Remember that if you increase or decrease the amount of water at 25 degrees centigrade, the ionic product Kw remains constant. But if you increase or decrease the temperature, the ionic product Kw changes. Hence, the ionic product of water at 25 degrees centigrade is Kw is equal to 10 to the power negative 14. Now let me teach you about pH, pUH, and prove that pH plus pUH is equal to 14. In the previous slide, we learned that ionic product of water Kw is equal to concentration of hydrogen ion and to concentration of hydroxide ion. Or I can write concentration of hydrogen ion and to concentration of hydroxide ion is equal to 10 to the negative 14, because the value of Kw is equal to 10 to the negative 14. Now I am interested to shift this negative 14 from power to coefficient. Can you guess that what should I do? Well, in mathematics, to shift any number from power to a coefficient, we need to take its log. So taking log on both sides, log of concentration of hydrogen ion and to concentration of hydroxide ion is equal to log 10 to the power negative 14. Note it down that log AB is equal to log A plus log B. So this is A and this is B. We get log of concentration of hydrogen ion plus log of concentration of hydroxide ion is equal to negative 14 and to log base 10. Also note it down that log base 10 is equal to 1. So I get this type of equation. To make this negative 14 positive, we have to multiply negative 1 on both sides. I get negative log of concentration of hydrogen ion plus negative log of concentration of hydroxide ion is equal to negative 1 and to negative 14. Now listen carefully. Instead of negative log, I put just P. So I get pH plus POH is equal to 14. This is the required proof. Here, let me ask you, what is meant by pH and what is meant by POH? Can you answer these questions? Well, pH means negative log of concentration of hydrogen ions, while POH means negative log of concentration of hydroxide ions. So remember these definitions of pH and POH. Also, you should note it down these important points. When pH of a solution is 7, then it is a neutral solution. When pH of a solution is less than 7, it is an acidic solution. When pH of a solution is greater than 7, it is a base solution. Each whole number value below 7 is 10 times more acidic, and each whole number values above 7 is 10 times more basic. For example, consider 3 acidic solutions A, B, C and 3 base solutions P, Q, R. Let the pH of A is 3, that of B is 4 and that of C is 5. A solution is 10 times more acidic than B solution. B solution is 10 times more acidic than C solution. What about A and C? Well, multiply these numbers. So A solution is 100 times more acidic than C solution. While here, let the pH of P is 8, that of Q is 9 and that of R is 10. R solution is 10 times more basic than Q and Q is 10 times more basic than P, while R is 100 times more basic than P. Thus note down all these important points. Finally, let me teach you numerical of pH and POH. Calculate the pH and POH of 0.001 molar solution of nitric acids. Well, we know that nitric acid is a strong acid. It means that it completely ionizes in water as when 0.001 molar solution of nitric acid is dissolved in water, it completely ionizes into hydrogen ion of 0.001 m and nitrate ions of 0.001 m. So the concentration of hydrogen ion is 0.001. Our concentration of hydrogen ion is equal to 10 to the power negative 3. Now taking negative log on both sides, negative log of concentration of hydrogen ion is equal to negative log 10 to the power negative 3. Negative log of concentration of hydrogen ion becomes pH, which is equal to negative 3 log base 10. We know that log base 10 is equal to 1, so I get pH is equal to 3. Now what about POH? Well, we know that pH plus POH is equal to 14. Putting the value of pH in this equation, 3 plus POH is equal to 14. Our POH is equal to 11. Thus the pH of nitric acid is 3 and POH of nitric acid is 11. I hope that you have learned all about pH and POH.
It's a building process. We start with very small items, we put them together, they start to interact with one another. We're going to talk about some of the different, again, terms of chemistry. The atom. Most of you had this in 4th grade, truly. In Michigan education track, that's about when it's introduced, 4th or 5th grade, and an atom is invisible. You cannot look at your skin and go, oh yeah, I see my atoms of my skin. No, that's not possible. It's invisible. We can look at its activity, believe it or not, with something that we use in the hospital called an MRI machine, because the atom has a central nucleus, which is made up of positively charged protons and neutrons, and then circulating around it, similar to moons around the Earth or to our planets around the sun, we have small negatively charged particles called electrons. And these negatively charged items actually, as we progress in the chapter, interact with one another to combine atoms of different elements to make up then molecules, compounds, which eventually become parts of our very microscopic cells. So, again, the atom is invisible. The nucleus is made up of positively charged protons and neutrons, and electrons are negative charges that orbit around the nucleus at different distances also. A molecule is a chemical combination of 2 or more atoms, the same chemical or combination of chemicals. So you could have a molecule of oxygen, and you could have a molecule of water, which would be a chemical combination of more than one particular type of element. A compound is substances whose molecules have more than one element. And we use formulas to describe the different elements within certain compounds. So, for example, sugar is C, which is carbon, 6 carbons. H, well, we have 12 of those, so we have C6, H12O6. And I apologize, those should be subscripted, but this particular font will not do that. And in your text, you can see the proper subscript of those number of atoms of certain elements in those compounds. So formulas describe which atoms are present in a compound, and then we describe them based on the numbers in that particular combination. So you've heard of H2O. Well, H2 would be 2 of hydrogen and 1 of oxygen. So that's what makes up water. Now, chemicals will bond, or elements bond, and atoms bond, and they do this to make their combination or their initial atom more stable. As I mentioned, electrons move around the nucleus in orbitals at different distances from that nucleus, and depending upon that distance, there are different energy levels. Some of these energy levels, or shells as they're also called, are able to share, donate, or borrow electrons until the outermost energy level is full, which is when it's most stable. An ion is an electrically charged atom or molecule which has available orbiting electrons. An ionic bond is a common type of bond where one atom that needs additional electrons to complete its outer shell receives from another atom those particular electrons, and your book describes this in a little bit bigger detail and more extensive detail, and you're welcome to read that. Sodium chloride is a good example of an ionic bond. It's also a good example of something we call an electrolyte, because an electrolyte is when you take something like sodium chloride, which is ionically bound, into solutions such as water, it will separate into charged particles. Charged meaning that it either still has an extra electron to offer or it's minus an electron in its outer shell. Some electrolytes that we're going to be talking about in reference to the human body include those like sodium, which is Na, potassium, chloride, CO2 or carbon dioxide, HCO3, which is bicarbonate, which is actually a buffer. We're going to talk a lot about our homeostasis and how important it is that certain of these electrolytes, and if you think of the word electrolyte contributing to the electricity of our body, when we start talking about how muscles contract, how nerves impulse, it will hopefully start to bring you back to that term electrolyte and thinking, for that charge, the charged particle to move, to make things happen, oh yeah, that's electrolyte, that's electricity. Kind of start putting those terms together in your head, because truly, and a much more complex, but I'm introducing this very simplistically, our entire body depends on our electrolytes for the movement of electrochemical impulse from one part of our body to another, and especially in the nervous system. Covalent bonds. Atoms that share electrons in their outer shell, such as H2, are covalently bonded, and this bond is a tight one. It doesn't usually dissociate in water, they're not easily broken, and they form all the major organic compounds that are in our bodies. Hydrogen bond is another type of bond, and it does not create new molecules, but instead it's a weak bond between neighboring molecules. Examples are DNA, and I apologize, I just saw a typo in here. It should be water. I don't know why that didn't spell check, but obviously where is a real word, but this should be examples are water, DNA, and proteins. Now, inorganic chemistry is the study of non-living matter, and organic chemistry is the study of living matter. Water is known as the universal solvent. We know that water is stable at room temperature, and it participates in many chemical reactions. All bodily functions lead to a breakdown of particles that dissolve in this water. We just gave an example of that as we talked about electrolytes. And then they become transported from cell to cell and organ to organ. There are a number of different chemical reactions, and once again, this is not a chemistry course. Those of you who have had inorganic chemistry or even organic chemistry know that you spend an entire year learning about how different chemicals react with one another based on their properties. One type of reaction that's described in your text is both dehydration synthesis and hydrolysis, and that has to do with the utilization of water in the reaction, and I do encourage you at least to read that portion in your text so that you're familiar with the terms. An important part about chemical reactions, especially in the human body, is they do involve some type of energy transfer, and in the process of transferring that energy, since energy can be neither created nor destroyed, it's transferred. When we say transferred, we mean it's sent into a different reaction or into a different mechanism within the human body. One element in the body, it's not really an element, it's actually a combination. It's actually a functional protein that is in our body that's really important in the chemical reactions that are taking place at all levels of human physiology are enzymes. Enzymes are that which speed up chemical reactions, participate in the reaction, but they themselves are not changed. And your book does give you a description of how sometimes they act like a key to facilitate an end product. We have enzymes that are utilized for digestion. We have enzymes that are utilized for the production of other substances within our body. Enzymatic activity is very important in homeostasis, as many of these chemical reactions are. And this is in the human version of enzymatic application. You probably have maybe watched a TV commercial where they'll talk about certain kinds of cleaning products that have certain kinds of enzymes that will make things work even better. So again, an enzyme will speed up a chemical reaction, participate in the reaction, but the enzyme itself is not changed. Some of the common elements you will want to become familiar with include H, which is hydrogen, Na, which is sodium, and by the way, these pluses are that which are charges. an extra positive charge. N, which is nitrogen, K plus, which is potassium, Fe is iron, C is carbon, O is oxygen, Cl is chloride, HCO3 is carbonic acid, and NaCl is salt, which I think you guys have probably been more than familiar with throughout your high school and middle school educations. Now, when we look at homeostasis, another very important term that you need to become familiar with and have a basic understanding of is acid-base relationships in our body. We have, as I mentioned, combinations where we have different molecules and different compounds that interact with one another. We have a representation of the amount of hydrogen that is actually present in a solution. The amount of hydrogen in that solution is given a number and a term called the pH. P, little baby p, and then the H stands for hydrogen. And the more hydrogen present, the more acidic that particular solution is. Our bodies will not function well if our pH is out of balance. Our chemical combinations will not work well. Our brains will not work well. Our hormones do not work well. Nothing works well in a other than normal total pH for our blood and our cellular or intracellular pH. Normal pH for the human body is 7.35 to 7.45. 7.35 to 7.45. To maintain a normal pH, there has to be an interaction and a balance between the acids in our system and the bases in our system. There should be buffers for excessive amounts of acid on a regular basis to maintain our pH in that normal range. In disease process, for example, if we do not breathe and we start to retain the acids that are left over because of the fact we're not getting rid of the excess waste, and or if our kidneys do not work well, either side of that picture will leave us in an altered pH state and usually acidic. Now you need to memorize that acids have a solution number or pH number below 7.0, and bases have a pH number that is above 7.0. So the normal human pH is 7.35 to 7.45 is slightly basic. The human body is just about ready to be unable to sustain itself for life when the pH falls below 6.9. You can resuscitate at that point, but there's a lot of damage that's done. So we know that's a very narrow range of the acid-base balance to maintain the human body within a normal pH. In your textbook, there is a scale that shows you the pH of different types of products, including stomach acid, orange juice, coffee, pancreatic juice, and household ammonia. And the further you get towards the higher pH, the more basic the product is. So if you look at something like stomach acid, it has an extremely low pH or an extremely highly acidic combination. Stomach acid being 0.8 for the pH on the pH scale. And we know that we like to keep our intracellular as well as our vascular beds at means that bloodstream flowing volume at that normal range of 7.35 to 7.45. When things are basic, they're also called alkaline. When we have a extreme alkaline product exposed to something like skin. So for example, once again, if you look at household ammonia, you know that if you pour ammonia on your skin, it doesn't feel real good. We know that even your skin likes to maintain a relatively normal pH. Anything too high or too low from that number will be extremely irritating. We'll talk a lot more about pH when we talk about the systems of transportation as well as the renal system, because both the cardiovascular system as well as the renal system is important for the maintenance of a normal pH in our serum. The other term you should be familiar with is the term lipid. Lipids are fats and or oils, and in our body we have certain kinds of lipids. You've probably heard a lot about, you got to keep your cholesterol levels low and you've got to keep your triglycerides low, but we surely don't have to keep them zero, because lipids are also essential as fatty acids for the production of certain hormones and for the regulation of certain chemistries in our body, as well as for the integrity of the cell membrane. Now, triglycerides are those lipids that are very helpful in storing energy. Phospholipids are products that are a fat, but they have something called a head and a tail, and if you look in your text, you can actually see the picture of the cell membrane, and they describe both the head and the tail in that pictorial. And the head attracts water and the tail repels water. Those phospholipids help to make up our cell membranes, and to stabilize that cell membrane or cell wall, we also have to have a certain amount of cholesterol. We also need cholesterol available, which we get via our diet, to make steroid hormones in our body, and there's a number of those that we'll also be talking about in the endocrine system. Proteins are another element in our body, and they are large molecules, and the basic unit of the protein is something called an amino acid, and in the amino acid, the base part of that structure is nitrogen. Now, the sequence of amino acids are held together by a bond called a peptide bond. The shape of proteins contribute to their role as either being structural or functional. Your book describes this a little bit more in detail as we discuss things like collagen versus something functional like an enzyme. As we mentioned before, an enzyme is a functional protein. Nucleic acids are a combination of chemicals that are essential for the structural formation of that which we've heard about so much in different TV shows and the rest, which is DNA and RNA. Nucleotides make up DNA and RNA, and they determine an individual's identity. A nucleotide consists of a phosphate unit, a sugar in the form of ribose, and a nitrogen base. In your text, they detail the names of the nitrogen bases. They are arranged in a certain sequence, and when you get a DNA probe study done on a particular patient, what you're actually finding is how those chemicals are actually sequenced in that particular individual. And based on the sequence of those chemicals, it determines who and what specifics are to that particular individual and their each and every individual cells. So even that you might have some shared DNA because you're half your mom, you will have a sequence that might be similar to hers, but it will not be identical. So we'll talk about the inheritance patterns later in the very end of the semester when it comes to combinations of DNA and RNA and how we express ourselves as individuals and how that determines the behavior of every cell within the body. That ends the very short and sweet, or maybe not so sweet to you, but the very short introduction to chemistry. Most importantly, become familiar with the terms. If you can also somewhat understand the basic nature of what those terms are implying, that also helps tremendously as we move forward, and especially in digestion, and once again in the very end when we talk about some of the genetics of the human body. So this ends the online Chapter 2 review on the PowerPoint, and our next one